The cosmic microwave background, or CMB, is like a snapshot of the universe when it was just a baby, about 380,000 years old. It's the afterglow of the Big Bang, and it carries a wealth of information about the early universe. But what if this ancient light could also shed light on one of the biggest mysteries in physics? Enter the Baryon asymmetry problem, which asks why our universe is mostly made of matter instead of antimatter. So, what's the deal with Baryon asymmetry? In a nutshell, it's the imbalance between baryons, which are particles like protons and neutrons, and antibaryons, their antimatter counterparts. The universe should have produced equal amounts of both during the Big Bang, but here we are, surrounded by matter. This discrepancy has puzzled scientists for decades. Now, let's talk about neutrinos. These tiny, elusive particles are known for their ability to change flavors as they travel through space, a phenomenon called neutrino oscillation. There are three types of neutrinos: electron, muon, and tau. As they zip around, they can morph from one type to another. This behavior is not just a quirky trait. It could be linked to the Baryon asymmetry problem through a process called leptogenesis. Leptogenesis suggests that in the early universe, heavy neutrinos decayed into lighter ones, creating an excess of leptons over antileptons. Leptons, which include electrons, are fundamental constituents of the atom. This lepton asymmetry could then be converted into baryon asymmetry through interactions governed by the electroweak force. So, how does the CMB fit into all of this? The CMB provides crucial evidence for the conditions in the early universe. Its temperature fluctuations reflect the density variations of matter and energy shortly after the Big Bang. These fluctuations are thought to be influenced by quantum effects, and they can help scientists understand why the universe is not a perfect mirror image of itself. This is essential for grasping the baryon asymmetry issue. When scientists analyze the CMB, they look for patterns and anomalies that could hint at the underlying physics of the universe. One of the key aspects of the CMB is its temperature anisotropies, tiny variations in temperature across the sky. These anisotropies can be linked to the distribution of matter and energy, including baryons and neutrinos. Recent research has suggested that the behavior of neutrinos in the early universe could have influenced these anisotropies. If neutrinos were oscillating and creating a lepton asymmetry, this could have had a cascading effect on the baryon asymmetry. The CMB might hold the fingerprints of these processes, providing indirect evidence for neutrino oscillations as a solution to the baryon asymmetry problem. Moreover, the CMB is not just a static relic, it carries information about the universe's expansion and evolution. As the universe cooled and expanded, the interactions between particles changed. Neutrinos, being so light and weakly interacting, played a unique role during this time. Their oscillations could have affected the dynamics of baryon production and annihilation, leaving a mark on the CMB. But it doesn't stop there. The CMB also reveals insights into the overall composition of the universe. By studying the CMB, scientists can determine the density of baryonic matter compared to dark matter and dark energy. This information is crucial for understanding how baryons behave and how they might have been affected by neutrino oscillations in the early universe. It's not just about what happened during the Big Bang, it's about how those events shaped the universe we see today. The interplay between neutrinos, baryons, and the CMB could be the key to unlocking the mystery of why matter dominates over antimatter. While the connection between the CMB and neutrino oscillations is still a topic of active research, the potential implications are exciting. If the CMB can provide evidence for neutrino oscillation as a solution to the baryon asymmetry problem, it could revolutionize our understanding of fundamental physics. It would mean that the tiny, nearly massless neutrinos played a significant role in shaping the universe's structure and composition. In conclusion, the cosmic microwave background is more than just a remnant of the Big Bang. It's a treasure trove of information that could help solve one of the most profound mysteries in physics. By studying the CMB and its relationship with neutrino oscillations, scientists are inching closer to understanding why our universe is predominantly made of matter. The journey to unravel the baryon asymmetry problem is ongoing, but with the CMB as a guide, the path forward looks promising. Who knows what other secrets the universe might reveal next?